Hi everyone, it's Mr. Corbin. I'm going to talk to you today about Chapter 8.2, which is how to find the area of a surface of revolution. So this is finding the surface area. So we talked about solids of revolution, and we've talked about how to find the volume of a solid of revolution. But now we're going to talk about how to find the surface area of basically the analogous shape. So this is going to be related very much to arc length. You're going to see the arc length differential in the formulas, and it'll make sense as why. So this is kind of in two parts. The first part is going to be a very technical part that's going to derive the formula, and then the second part we'll do some examples to show you how to use the formula. This can get pretty complicated. The integrals that result end up getting pretty complicated. The good news is that the formulas will be on the formula sheet on the midterm, so you don't have to memorize the formulas. It's a little weird because there are sort of kind of four different cases. It gets a little complicated, but it's basically the same formula, just with really, really minor adjustments depending on whether you're revolving about the x-axis or the y-axis, or depending how the curve is given. So I'm going to go through the derivation for the most basic case, which is we have a function of x and we're revolving about the x-axis. So that's the most basic case, and I'll talk about how we derive that formula, and then basically I'll just wave my hands and say, and it's the same for the other four cases. It's the same derivation, just changing x's and y's and doing things like that. So the main part will be doing the examples, and we'll get to see some techniques for how to do that, because that really is the hardest part. All right, so what is the surface of revolution? So when we have a surface of revolution, we're starting with a curve, and we're rotating it about a line, and this is the lateral boundary of a solid of revolution. So for a solid, we're taking the region, revolving it around the axis of revolution. Here, we're just taking the curve and revolving it, and so that gives us a surface. All right. Basically, we're defining surface area as, how much paint would it take? So if we have a flat region with area A, it takes a certain amount of paint. If we have a curved region and it takes the same amount of paint, we want it to have the same area. So we're going to start with some basic ideas, which is going to be a cylinder and a cone. So these are going to lead up to how we define our formula for surface of revolution. So we want to look at the lateral surface area of the cone. So the lateral surface area is the surface area of the curved part. We're not including the bases. So we're not including the top and we're not including the bottom, but just the surface area. If you think about it like a soup can, it's what's the area of the label that goes around the soup can. Well, if we imagine cutting the cylinder, or peeling the label off the soup can, we know that the height of that rectangle is going to be the height of the cylinder, and then in terms of the width, we can find that by noticing that it's the same as the circumference of the base, and we know if the base has radius r, then the circumference is 2 pi r. So the lateral surface area is 2 pi r times h, or 2 pi rh. Okay, so that was for a cylinder. Cones are a little bit more complicated, but we can get the same basic idea. For a cone, when we cut it and we unroll it, what we get is we get a sector of a circle. And the radius of the circle is L, and L is called the slant height of the cone. So we can find the, so since we know the radius of the sector, we know the arc length of the sector, so we can find the angle theta, because we know that there's a formula for arc length of a circle, which is arc length equals r theta, where theta is in radians. So in this case, we don't know theta, but we know that the arc is 2 pi r, and we know that the radius is L. So theta equals 2 pi r divided by L, which we see right here. So that helps us find the central angle. And once we know the central angle, we can actually find the area. So the area of a sector, I'm sure this will be on the next slide. So the area of a sector is 1/2 r squared theta. So in this case, my r is L. The radius of the sector is the length. And then theta is 2 pi r over L. Well, hey, conveniently some stuff cancels. 2's cancel, one of the L's cancels. So the area is just pi r L. So that's really convenient that we've been able to define the lateral area of a cone in terms of the slant height and the radius. So that's really super convenient. So I'm going to go to the next page, and it'll probably still be there. Yep, there we go. All right. So now those are the two basic ones, and there's one more complicated one that we want to deal with. So the idea is, since we're starting with a curve, we want to approximate that curve by a series of connected line segments, which they're, again, calling a polygon, which technically is wrong because it's not a polygon if it's not closed. But it's a bunch of connected line segments. So we're going to use that to approximate the curve. And then when we rotate it, we get a bunch of, little linear things that created a nice little surface. And so the question is, how do we determine, the question really is, how do we determine the surface area of each of those little surfaces? Okay, I have to pause for a quick second because I forgot to do something. Just put the do not disturb sign on my door, so I don't want them to come in and start vacuuming or something. So I'll be right back. Okay, sorry about that. All right, so as I was saying, we're going to use those connected line segments and rotate them in order to get a simpler surface that we can find the area of, and then as we take the number of segments to infinity, and we take the limit and we add it all up, we get the exact surface area. So the basic shape for the approximation when we do that revolution is called a band. And you can think of a band sort of like a rubber band, except that a normal rubber band, is technically a cylinder. Whereas these bands, because the segment that you're rotating, there we go, might be slanted. So when you revolve it, you're going to get kind of a slanty band. And if you think about it, it's kind of like a cone with the top cut off, which is called a frustum. So we're finding the lateral surface area of a frustum. So really, we need to be looking at cones and not cylinders. So here they have the lovely diagram of what a band looks like. Bands are essentially a portion of a circular cone, and the key being that we have a slant height L1, we have a slant height L for just the frustum, and then R1 and R2 are actually going to be pretty easy to handle. So what we're going to do is we're going to look at the difference of the two. We're going to look at the difference of the two surface areas. We're going to look at the surface area of the large cone, and we're going to subtract the surface area of this phantom cone up top. So we're going to take the surface area of the whole cone, and we're going to subtract the surface area of this cone, and then everything is going to be great. And we're also going to use similar triangles. So here comes the big technical part where I explain to you how we find the surface area. Okay. So what we do is we subtract the area, and so the area is pi times R2, which is the radius of the big cone, and then the slant height is L1 plus L, and then I'm subtracting pi R1 L1, and if we factor that, we get pi times the quantity R2 minus R1 L1 plus R2 L. So that's fine. But now we're going to use the fact that the two cones are similar And so we have similar triangles hiding within the cone. I'm going to go back really quickly. So what we have here is we have this triangle right here. And then we have the big triangle right here. And these two triangles are similar. So what I can say is that the ratio of the sides, so I'm going to do this the right way. So if I have L1 over R1, that has to be the same as L1 plus L over R2. So we're going to take this equation, which comes from similar triangles, and we're going to manipulate it. I don't know why that happened. We're going to manipulate that equation in order to find something, in order to make a substitution into that area formula that's going to be nice. Keeps like doing that little jerk to the side when I'm done. I'm pretty sure that's just me being silly. Whoops, let's try that. Okay, there we go. So we have that equation, which I had just written on the previous page. So R2L1 equals R1 L1 plus R1 L. But really what we're going to substitute for is we're going to substitute for this if we can. So by just manipulating, we have R2 minus R1 L1 equals R1 L. So we have pi, and then we have R1L plus R2L. So that's really convenient because now I can factor out the L. And it turns out that the surface area is just the... You just have to add the two radii together and multiply by the slant height of just that piece. Now, we don't want to deal with R1 and R2 in the formula. So what we do is we actually take the average of them. So we're going to say that R, we're going to hope that my pen decides, hey, like maybe I should actually work now. So we're going to say that R is R1 plus R2 over 2. So R is the average radius. Put those little close together, but you get the idea. So we're going to replace R1 plus R2 with 2R. So that gives us the area 2 pi RL. Okay. And the reason why we want the average radius is because we want to take one sample point in each interval. If we're looking at R1 and R2, we're looking at the two endpoints of each interval, and that doesn't let us do a sample point, and we need to do a sample point in order to do an integral. But again, we are going to be allowed to use that sample point to make it work. All right. So now let's take a look at our strategy. So here we have this lovely curve here, y equals f of x. And we've revolved it about the x-axis, and we've created this lovely surface of revolution. We need f to be positive. We need f to have a continuous derivative. So we're going to look at a little slice, as you can see here. And we want to find the surface area of just this one slice. And then we're going to add all the slices up. Take it to infinity. Excuse me, pardon me. It is early in the morning this time. Also, this is one of those diagrams that I'm actually trying to figure out which way you're supposed to read it. I don't know which way the band is actually going. That's probably that way. Anyway, I can't remember what they're called, but it's the thing where you can look at it two different ways, and it's like the cube is either coming towards you or the cube is recessed. And your brain keeps switching back and forth. I can't remember the name of the phenomenon, but it's really interesting. So I'm having the same problem with this band. It's like, which part is the front? Is this part the front, or is this part the front? And my brain keeps switching back and forth between the two. I think by the dotted lines, this part is supposed to be the back, and this is supposed to be the front. But my brain is constantly switching back and forth between which way is right. It doesn't actually matter. I just think it's interesting. All right, so we're going to divide up into subintervals, blah, blah, blah. We're basically going to do arc length, essentially, except then we're going to plug in for the area of the band. All right, excuse me. So let me explain the part of why we need to do arc length here. So this part right here, that's our L. Okay, that's the length of that's the slant height of the frustum. And this right here, yi, that's going to be our r. That's our radius that we're using. And the one thing to note is that yi is f of xi. Okay, so we're going to use that. That's going to come into play. And so we're going to use this idea of 2 pi lr. So in order to find L, we're doing the arc length. Okay. So here's what we go. Here's where we have. So the slant height is L, which is the length of the thing. So we just plugged into the formula, and this is the area. All right, so that's the surface area of the band. And then this is from the arc length formula, or the arc length derivation. So we're going to substitute this into here. And then this is the average radius. So we did that. So here we go. So xi star is some number here. So that's just like so it says as in the proof. That's as in the proof for arc length. Okay. All right, so essentially, so we have 2 pi, this is my L, and this is my R. Okay. Alrighty. So there we go. Great. All right, so let's move on to the next slide. When delta x is small, we have yi equals f of xi, which is approximately f of xi star. So remember, xi star is that specific point that we need to take. Xi is not necessarily that point, but the idea is it's close enough. And this is where there's a bunch of technical analysis things about continuity that we have to say. All right, so essentially this formula magically turns into this. So we have 2 pi f of xi star root 1 plus f prime of xi star squared delta x. So that is the area, that's the surface area of one band. I guess technically it's the lateral area. Okay, so now I take n to infinity, add them all up. That's what's going on here, and we see, hey, look, it's an integral. It's a Riemann sum, so it's an integral. And so this becomes our definition of surface area. So this right here is the definition of surface area that we're going to use. So the surface area is the integral from a to b, 2 pi f of x, root 1 plus f prime of x squared dx. Key is that we are revolving about the x-axis for this formula. This is the formula where we are revolving about the x-axis. So that right there, S, is the key formula that we need. All right. Now, if for some reason our function is defined in terms of y instead of in terms of x, so we have a function of y, and we have x as a function of y, it turns out that basically the same thing works. So here we have Leibniz notation. So this is just putting it in different notation. So as I was saying, if the curve is described as x equals g of y, then here's what changes. What changes is the limits change, because now we're integrating dy. And instead of dy dx, we're integrating dx dy, or instead of using dy dx, we have dx dy squared under here. This y stays the same. Note, this is still a revolution about the x-axis. Even though we're integrating dy, it's still a revolution about the x-axis. This is like one of those very, very crazy situations that just doesn't come up very often. So then what if we want to do a revolution about the y-axis? Well, we'll see basically things change. Like everything is basically the same. The only difference if we're revolving about the y-axis, then instead of y in our integral, we have x. So that's the key difference there. If we're revolving about the y-axis, we have x in our integral. Now, one very common way to see this notated is like this, because ds, remember that's the arc length differential. And since it appears in there in either form, you can use either form for this. Oftentimes you'll see it notated, you'll see surface area notated in that way just to make it a little bit more compact. Just to make the definition a little bit more concise. So also that you can see the parallels and how arc length connects to surface area. In terms of technical things, like I write it all out on the formula sheet, but that's just the connection there. Anyway, I think that's all the technical stuff. So now it's probably time to do some examples. So now that I've explained where this formula comes from in painstaking detail, it's time to do the examples. They want to show this concept, because apparently I forgot there's this concept slide, which is good because I like concepts. The idea is, if you're revolving about the x-axis, then if you think of one particular point on the curve, you're counting the circumference of the circle that's being traced out by that. And y, if you're revolving about the x-axis, then the y value of that point is the radius that you're using. And then similarly for the revolution about the y-axis, x is your radius and the circumference is 2 pi x. Okay, so that's one way to remember the formula. All right, so here we go. So we're going to look at the curve y equals square root of 4 minus x squared from negative 1 to 1. It's an arc of the circle x squared plus y squared equals 4. Yep. And we're going to find the area of the surface obtained by rotating this arc about the x-axis. So this is part of a sphere. So this is the surface area of a sphere with like the two ends cut off. So we're going to find the surface area of it, and so we're going to use the surface area formula. So the first thing we have to do is we have to take the derivative. So dy dx is 1/2 blah 4 minus x squared to the negative 1/2 times negative 2x, so that's all chain rule. When everything gets simplified, you get negative x over root 4 minus x squared. Again, just like with arc length, surface area problems are rigged. They basically have to be rigged in order to do them, because otherwise they get nasty really quickly. All right, so we're now ready to plug this into the formula for surface area. So we have S equals the integral from negative 1 to 1, 2 pi y, remember y is going to be our f of x, and then we have our arc length differential. So this, it would help if I was writing on the tablet and not on the tablet protective cover. So this is going to go in for here, and that's going to go away. So that's going to go in for there, and then my y is root 4 minus x squared. So that's just my function. All right, so that's how we're going to make those substitutions, and then we're going to have to do some tricky algebra, but it's okay, it'll work out. All right, so we made those substitutions. We brought the 2 pi to the outside, squared everything, did all that fun stuff. All right, this is where things get crazy. This is where the algebra gets really complicated. I like to say that students who have trouble in Calc 2 don't have trouble with the calculus, they have trouble with the algebra. And this is one of those algebra times where it's like, I'm going to do a whole bunch of algebra stuff, and it's going to make it super simple and really easy. And it's like, if you don't see the trick, or if you mess up the algebra, or you aren't sure how to do it, that's what's going to hold you up on this problem. So what I notice is I have two square roots being multiplied by each other. So I'm going to bring them together under a single square root, and then I'm going to have to distribute. and things are going to cancel out, and it's going to be amazing. All right. So first we did that. So first they created a. So the first thing they did was they changed this 1. So I'm going to go back. I'm back on this slide right now. So they decided to do it a slightly different way. They combined like terms, or not combined like terms. They created common denominators and combined the fractions underneath the second square root first, but that's fine. So 1, they're rewriting it as 4 minus x squared over 4 minus x squared, which is totally fine. I would have done it slightly differently, but that's fine. So they made that substitution. And then they combined things under the fraction, and what we notice is, hey, like there's a negative x squared and a positive x squared, so they're going to cancel out. All right. And then on the top, you're left with just the square root of 4, which is 2. And now I have this lovely root 4 minus x squared over root 4 minus x squared, so those are going to cancel out. And I'm left with just 4 pi integral from -1 to 1 of 1 dx. And that's 2. So it's 4 pi times 2, which is 8 pi. So even though it looked like a really nasty problem, it turned out to be completely rigged, so that the solution came out very easily. So, which is, I guess, not too terribly surprising, since it is part of a sphere. All right, so that's how we do that one. So that one is a weird example because it's really easy. So now let's do a harder one where we actually have to do some integration work. All right, so we're looking at example 3. We're finding the area of the surface generated by rotating the curve y equals e to the x between 0 and 1 about the x-axis. Yeah, by the way, I pretty much stick to the x-axis here. There's not really a good reason for me to go to the y-axis. It just adds a bunch of extra confusion. All right, so we're going to have to take the derivative. Okay, dy dx equals e to the x, and now we're going to substitute. So we have 2 pi y, blah, blah, blah. So we have 2 pi integral from 0 to 1, e to the x, root 1 plus e to the 2x dx. Okay, so now we're going to have to do some fancy stuff. Actually, no, we're not really going to... let's see, we might have to do something a little fancy. I think we have to... All right, so we made a u substitution, which, yeah, they did it weird, but that's fine. All right, so we're going to make the u substitution u equals e to the x. Excuse me. So we made that u substitution. So now I have root 1 plus u squared du. And now I'm integrating from 1 to e. All right, so how do we do this integral? Well, you'll notice that this looks like a trig substitution because I have root 1 plus u squared. So that's the next thing I'm going to do is I'm going to make the substitution u equals tangent theta. So this is weird. So let me explain what happened here. So we went from here to here. So we made the substitution u equals tangent theta. Du equals secant squared theta d theta. So then I had 1 plus tangent squared theta, which is secant theta, because it's under the square root, and then times secant squared. So that's where the secant cube comes from. When u equals 1, theta equals pi over 4. When u equals e, I don't know the arctangent of e. So I'm just going to call it alpha. So they call alpha the arctangent of e. So that's where this alpha comes from here. Okay. So this is a common technique when you end up making a u substitution and you get some value that you don't know. Say, I'm just going to let it be whatever it is. Alternatively, I mean, this basically means you're not going to use these limits, so I would have just kept them as u limits and said u equals, but that's it. All right, so now we have to integrate secant cubed, and this is one that we did in the textbook already, so my guess is they're probably just going to use the fact that we've already done that problem, which they do. So they've used a previous result that we've got by integrating secant cubed before. This is not one that you're expected to memorize, but clearly they're like, it comes up a lot, so they just keep using it. All right, so they have that. We see we're going to get some cancellation here. Alrighty. So now what we have is they've substituted alpha. Again, why they substituted alpha, I have really no idea. I think that was a really silly move, but you know what? I'm not in charge. So what we're going to do is we have alpha equals the arctangent of E. So I'm going to set up a situation here. So this is alpha. And tangent is opposite over adjacent. So this must be E over 1. And then this is going to be the square root of 1 plus E squared. By the way, that alpha is totally wrong because E is greater than 1. So that's totally fine. But this helps me find the tangent of alpha is E, but this helps me find the secant of alpha. So secant alpha, because secant is hypotenuse over adjacent, because it's 1 over cosine. So that's just root 1 plus E squared. All right, so then we make that substitution. They did it a slightly different way, but I did it with the triangle, which was totally fine. And you get this lovely hot mess of a thing. This is the surface area. This is the exact surface area. And you can see that it's a lovely, lovely hot mess. And you can see that there's no way to simplify it. It's just that lovely hot mess. The point that I wanted to make with that example was that sometimes when you are doing a surface area problem, or you're doing one of these other problems, you still have to make a trig substitution to get to the final to get to the final answer. So it's not just, oh, I know the formula and then I'm done. Like, all the techniques that we learn in the first part of the course are really relevant for the things that we're going to continue to be doing, particularly the trig substitution and the partial fraction decomposition. The trig integrals don't come up so much. Integration by parts sometimes. That sometimes comes up with some of these problems because we do have the original function, and then we have something else on the outside. So sometimes there's an integration by parts thing you can do there, but that's a little bit less likely. Anyway, so that's all I have for you today regarding surface area. I was like, what am I teaching today? And so we learned the formulas for surface area. We did some examples to see how it works. I'm sure that you can see that there's a very big ramp up in difficulty. So it starts with like, oh, the super easy problem where everything cancels, and then it goes to the super complicated problem where I make a trig substitution and a bunch of other hot mess, and I get an answer that is just mind-blowingly complicated. Yeah, that's kind of how this goes. And so you'll find that the WebAssign problems are going to have both of those extremes in them, and then there will be a few in the middle where it's like, oh, I have to do a little bit of algebra inside the square root, but then I get something that I can work with. So just keep plugging at it with the algebra, keep going back to the examples in the book, use the videos, so that you can start to see some of the techniques that are being used. So that's all I have for today. Thank you very much for watching, and I will see you all next week.